So what's the first thing we want to do with this one? Vertical asymptotes, all right, that seems reasonable. All right, so anything we can do without the derivative, right? Vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts, all that good stuff first. So vertical asymptotes sounds good. White is not a good color to write with on a white background. So we got x squared over, if we factor that, x minus 2x plus 1. Are there any holes, first of all? Anything that cancels from the numerator and the denominator? No, okay, only the vertical asymptote. So we have vertical asymptote at x equals 2 and x equals -1. Yeah, everybody good with that? Perfect. No, not good with that? Or are those old no's in the chat? Hopefully you're all good with that. Okay. Next thing would be x-intercepts and y-intercepts. So first off, we can set the numerator equal to 0. And that tells us what? That at x equals 0, y equals 0. So there's our y-intercept and our x-intercept. True? Obviously, we're not going to have any other y-intercepts. Is it possible for us to have any other x-intercepts? Possible, but do we have any? No. Right. Okay. What about horizontal asymptote? Since the degree of the numerator and the degree of the denominator are the same, and this is a rational function, we can divide the leading coefficients. So that should be y equals 1 in both directions. Everybody good with that? So what's the next thing we need to do? Oh, now you can just use that rule, Nick. That'll be fine. All right, increasing, decreasing, maxima, minima from the derivative. So we'll take our derivative at prime. Should be x squared minus x minus 2 times 2x minus 2x minus 1 times x squared all over x squared minus x minus 2 squared. Everybody good with that? I hope. Yeah. If we simplify that, let's see, that's going to be 2x cubed and then a minus 2x cubed. So those are going to cancel. Then we're going to have a minus 2x squared and a plus x squared. So that'll be a negative x squared and then a minus 4x all over this x squared minus x minus 2 squared. Everybody good with that? And we can take out the, well, first off, we can see if there's any places where this equals 0 and any places where it's undefined. It's never going to be undefined anywhere where we are defined for our original function, right? Because we have the same denominator, it's that it's squared. So we're not going to have any places where the derivative is undefined, but we can find some places where it equals 0. So we can take out the negative x there if we want to have negative x times x plus 4. And so our derivative is equal to 0 when x is 0 and when x is -4. And on a sign chart, -4 and 0, you put something in the middle like -2. Negative 2 is going to give us a positive times a positive. Oh, sorry. Shouldn't be this. It's just negative 4 and 0. What else do I need to put on here? Haven't done a rational function one of these in a while. What else needs to go on here besides negative 4 and 0? Yeah, our undefined values, so negative 1 and positive 2. So if we plug in something between our negative, well, let's say between negative 1 and 0, like negative 1/2, we know the denominator is always going to be positive because it's squared. So we just need to look at the numerator. So if we plug in negative 1/2, that's a positive times a positive. If we plug in something between 0 and 2, like 1, that's a negative times a positive. Something greater than 2, that's a negative times a positive. Something between negative 4 and negative 1, like negative 2, that's a positive and a positive. And something less than negative 4, like negative 1,000, that's a positive and a negative. Is everybody good with that? I hope. All right. Then we need to find the second derivative. What was it? X squared minus x minus 2 squared. So that was f prime. So f double prime, we use the quotient rule again. Probably should have given myself a little more room here, but I didn't. So that negative x squared minus 4x is multiplied by 2 times x squared minus x minus 2 times 2x minus 1. And what can we factor out of those? So x squared minus x minus 2, right? Leaving us with x squared minus x minus 2 times negative 2x minus 4. And then minus 2 times 2x minus 1 times negative x squared minus 4x. Ran out of room there too, 4x. And all of this, I didn't put it on the first one, but all of this is over x squared minus x minus 2 to the 4th. So I should be able to cancel that out with one of these to make this a third power. And then simplify the inside. So that'll be negative 2x cubed plus 2x squared plus 4x minus 4x squared plus 4x plus 8. And our other piece of it here should be, let's see here. We distribute the minus, no, yeah, how do we want to do this? Let's just make this minus 4x minus 2 times negative x squared minus 4x. Still over the x squared minus x minus 2 cubed. And now we've got negative 2x cubed, and this is going to become a positive 4x cubed when I distribute that through. So that'll give us a 2x cubed. We're going to have a negative 4x times a negative 4x, which is a 16x squared, and then a minus 2x squared. So that's 14x squared from over here, minus 4x squared, plus 2x squared should be plus 12x squared. And then we're going to have a minus 8x here. So plus 4x plus another 4x. Looks like that should cancel out. And then we've got a plus 8. Everybody good with that derivative? That was fun, huh? Any issues with that? All right, now, did anybody, when they did this on their own yesterday, does that numerator factor nicely or no? I have a bad feeling that it probably doesn't, but. How many of you actually did this yesterday and can answer that question about whether that numerator factors nicely? I don't think it does, but I just did it on Desmos to figure out what it was. At about negative 6.107. So if I put that on my chart, along with my undefined values, or the -1 and 2, then we should be able to test all of these intervals. I mean, whether you did it differently or not, it would still require the same numerator to solve at the end. Right. Yeah, it's the same. I mean, same thing, except I canceled out the x plus 1 times x minus 2, and factor a 2 out of this, it's x cubed plus 6x squared plus 4. They all have the same roots as 2x cubed plus 12x squared plus 8. It's all the same. Anyway, something less than -6 is like -1,000. If I plug in -1,000, this denominator is going to be a positive number, because -1,000 squared is much larger than the -x and the -2. And we're going to cube it, so stay positive. And then in the numerator, it's going to be a negative, it looks like. It's a negative or positive. Something between -6 and -1, like -2. If I plug in a -2 down here, that's going to become what? Looks like that's a positive still. And down, or up here in the numerator, that's going to be a positive. So still concave down. Something between -1 and 2, like 0, is going to give us a negative also. And something greater than 2, like 1,000, is going to be positive over positive. Good or no? So now all we have to do is plot our points and graph it. I feel like we got an issue over here with this, these two negatives here. Yeah, I was just thinking, I think we got an issue with those. I think that one's positive. And I think the other one should be positive too, but maybe I just did some bad arithmetic. Seems like that's all right. Okay. Yeah, -2. Yeah, okay, that makes more sense. Okay. All right. So if we're going to plot all these points, first off, we're going to need the point at -6.107. I can guarantee you it's just a little bit over 1. So right there. This value at at 0 was a local max. So we know we're going to be concave down inside of there. like that, approaching those asymptotes. We might want a value over here, like 1, 2, let's like plug in 3 to our original function. If we plug in 3, that should give us 9 over, what, 9 over 4. And we're concave up for all of that and approaching our asymptotes. And then same thing over here. Somewhere over there, we're going to be concave. It's concave up. We're going to approach that asymptote. I didn't plug a point in, but that's basically what this graph is going to look like. Now, I didn't put in my local min there at -4, did I? Let's fix this. So at negative, yeah, at -4, what do we get if we plug that in? 16 over what? 18? Just under 1, yeah. So we got a little min, and in fact, this value, now that I think about it, this value is actually just a little bit under 1. So what we do is we come down here and we are concave up, crossing through our asymptote, and then going back up and then changing to concave down and approaching that asymptote from below. I know my picture doesn't look real great, but that's what it's supposed to be doing. So it should be crossing through your asymptote, hitting this min, which I didn't do a very good job of making that look like a min, but then becoming concave down and approaching the asymptote from below. Does that make sense to everybody? Everybody good, yeah? I probably won't make you do one as annoying as that, but you should be able to find all the intervals easily enough. All right, let's look at a parametric function. So we've got a parametric function, x of t is equal to t cubed minus 12t, and y of t is equal to 1/3 t cubed minus 2t squared minus 12t plus 1 for all real numbers t. So we want to find the highest, the lowest, the leftmost, and the rightmost points of this parametric function. Any thoughts on how we're going to do that? All right, so yeah, the max y and the min y should be our highest and our lowest points, right? And then the same for x. The max x should be our rightmost point, and the min on x should be our leftmost point. Everybody good with that? Or no? Conceptually, hopefully that makes sense. All right, so let's go ahead and do that. Which one do you guys want to do first? X, everybody seems to want to do x. All right, x it is. So how do we find the min and the max of x? We need to find the derivative. Okay, so we need to find the derivative of x. So we're looking for dx dt to find the rightmost and the leftmost, right? Because dx dt will tell us at what t value x is at a max. So dx dt should be 3t squared minus 12. Okay. And if we factor out the 3, that becomes t squared minus 4. That gives us t equals plus or minus 2. Is where it should be at its right or leftmost, potentially. What do we need to do with that? Make a sign chart. Yep, -2 and 2. 1 second. Okay, sorry about that. All right, so if we plug in 0 into our derivative, what do we get? We get a negative, right? If we plug in something greater than 2, what do we get? Like 1,000 or something. What should we get? Positive. And if we plug in something into -2, what do we get? Or sorry, something less than -2. We should also get a positive. So what is this telling us? It's telling us that this function from -infinity to -2 is moving to the right, right? And then it starts moving to the left again. And then it starts from -2 to 2, it moves to the left. And then from 2 to infinity, it's moving back to the right. Everybody good with that? Or no? Yeah? So if it's moving to the right from -infinity to -2, what is the what's happening as it goes towards -infinity? Let's ask that first. Right. If we go towards -infinity, it's moving to the left. So that value is getting a larger and larger and larger negative value as we plug in larger and larger negative numbers. So we know that it's starting all the way over at -infinity, and it moves to the right till you get to -2. Okay. And then it stops moving to the right, and then it starts moving back to the left from -2 to 2. Well, is it ever going to go, as it goes left, is it ever going to go past -infinity, where we were going towards as t goes to -infinity of x of t. Right? This is -infinity. Right. These are just local mins and maxes here, Adrian. That's correct. So we're gonna talk a little more about this. As t goes towards infinity, of x of t, it's going towards infinity. So we should know that there shouldn't be any absolute mins or absolute maxes of the x values on this graph. But if I'd restricted it to some specific values, like from -5 to 5, then we certainly would. Okay. But since there's no restrictions on here, we need to look at the limits as x of t goes to, or as t goes to -infinity and positive infinity of x of t, to see that it's always going to -infinity to the left and positive infinity to the right. But we do have a local max and a local min here at 2 and -2. But we're not concerned about that. We just want to know what are the highest, the lowest, the leftmost, and the rightmost. So in this case, we don't have a rightmost or a leftmost. Does that make sense or no? We're going to do some in a minute where we have restrictions on the domain of it, or we will for sure find some. But everybody good with that? All right, what about dy dt for the highest and lowest points? Dy dt should be what? T squared minus 4t minus 12. And that should be t minus 6 and t plus 2, if we simplify that, right? And we get t equals 6 and t equals negative 2. Okay. So those are the places where we could be having absolute or local maximum minima. So we'll make a sign chart with those. Put in 0, you get a negative, right? And put in a positive like 1,000, you get a positive, and you plug in negative 1,000 and you get a positive also. Good or no? Okay. And so we still need to do the same thing. Let's look at the limit as t approaches negative infinity of y of t. What do we get? Negative infinity, so it's going down forever. And what about the limit as t approaches positive infinity of y of t? Should be infinity, and once again, we're not going to have any absolute maxes or mins, highest or lowest points, but we do have some local ones. So we know that there is a local minimum of the x value, sorry, a local maximum of the x value at -2, a local minimum of the x value at x equals 2, and a local maximum of the y value at t equals -2, and a local minimum of the y value at t equals 6. Good or no? So let's take a look at the graph of this. Maybe. Let's try this again. There we go. What do we have? T cubed minus 12t and 1/3 t cubed minus 2t squared minus 12t plus 1. And so if we were to look at this from, we'll just put in like negative 1,000 and 1,000. We're going to need to shrink this out a little bit. This is what the graph looks like. Okay. And we can see, if we zoom in a little bit here, that here is that local max of the x value, and it's the local max of the y value, right? And we can see it from our work that those both occurred at the same t value. Here's the local min of our x value, and here, somewhere over here, is the local min of our y value. Everybody good with that? Or no? Let's see, one of them was at -2, right? You can see at -2, that's that upper point, and that furthest right point before it comes back around, sweeps back around and goes the other direction. Any questions or issues with that? No? All right, good. I guess we're going to stop there. I wanted to do more today, but that quiz took longer than I thought it was going to. So we'll do the more of the leftmost, rightmost stuff tomorrow. I'll put up an assignment today with some practice on the graphing and finding the max and the min and all that stuff for the regular functions. For non-parametric functions, we'll do more of the parametric ones tomorrow. Sound good? All right. If you had any issues with the quiz for some reason, just stick around and we can talk about them afterwards. Otherwise, I'll post that assignment up sometime later this morning when I get a chance between classes, hopefully. See you all tomorrow.
Thank you, Mr. Short.
You're welcome. Have a good one.
Thank you.